I'm going to do a sketch first. How many elements do we have? 6. So how many nodes are we going to have? 7. You add 1, Tyler. Add 1. Add 1. And what is each element going to look like in our sketch? A resistor. Thank you. You've taken heat transfer. No, that's fine. So you're going to have 6 resistors. So the resistors, basically, if you think about it, a resistor resists heat, right? Or resists electricity, where in these cases they resist heat, okay? All right, how many do I have? 1, 2, 3, 4, 5, 6.
You can straight down, no matter.
I would do a cross like this, because that's how this wall is, yeah. We will, but you're getting ahead of yourself. So, I don't think the new students in heat transfer, or no new students, the students in heat transfer right now, have you done this yet?
No.
Okay. I can't remember. Okay. So each section represents a resistor, or it's resisting heat. Okay. So
What were the 2 terms? The node and the
element. So there's 6 elements and 7 nodes in this case. What are the boundary conditions? And the inside temperature, right? So T1 equals what? 20, right? 20. And T7 equals? 70, yes. Thank you. T infinity.
No, well, I just thought you were talking about.
Actually, it wouldn't be T infinity, right?
Well, see, I was wrong there, but that was the answer.
Oh, yeah, it is. Yeah, sorry. I was thinking it was the wall, but yes, you're right. So, let's see. I need purple here. Element 1. What are the 3 modes of heat transfer?
convection, radiation.
Yep. Don't worry about radiation. So what is element 1? Convection. Yep. So, yep, and then,
touching, right?
say that again?
Conduction is the touching.
Yep. So do you know that convection is really conduction? Because the fluid molecules are touching each other, but it's to do with gas, right? Yep. Or liquid. So technically there's only 2 types of heat transfer. Conduction and radiation, but it is, and we'll get to that. So the rest are conduction. And element 2 is, let's see, the siding, the wood, right? Because this is, element 1 would be outside. Element 6 would be inside. All right, what's next here? So let's just have this area would be 150. Am I writing big enough? Okay. Much bigger than the TV.
What is the area of exposed area, like this box, or the whole?
It's the
Just the fan, right? In this metal part.
it's the area is the actual, like, if we looked at, it's this area here. That's kind of what they're saying.
Oh, so
It's
the
like if
side
you
of it?
sliced it in half and you ripped it apart.
Can you just make a little line like where you would slice it? Like you're talking about like that? Way?
Yes, yes.
Like right through there?
Yep, and down and the back and off. Yes, that's the area they're talking about.
Okay.
Because that's the way the heat transfer is going.
Oh.
Yep.
I just couldn't figure the air was going up into like a hood or something and then blowing across those fins.
It's,
I just couldn't tell
It's-
from the picture. What's
yeah, the
going
heat
on.
transfer is going to go through the wall like this.
Okay.
So we're going to find the temperatures. What are some assumptions? Yeah, no radiation. We have boundary conditions. Do we have initial conditions? There's no initial conditions because we're going to assume that this thing is always going to have that same temperature forever. So what does that mean? Steady state, yep. All right. So here's the solution. So we're going to do this two different ways. The first way is we're going to kind of develop equations for each element with the heat transfer, okay? And then I'm going to show you the other FEM way that's easier with the stiffness, okay? Questions so far? Okay, so let's assume a solution for conduction and convection. So conduction. See if you remember these. What's the conduction equation? And what's it called? What is it? Well, that is a heat flux, but what is the basic definition called of conduction? Something law. What? No, not Hooke's. Starts with an F.
Fundamental heat transfer.
Not Faraday. That's capacitance. Fourier's law.
Oh, that other guy.
Oh, yeah.
This other guy. So anytime you hear Fourier's law, it's conduction, right? And do you remember that equation? LA? No?
This could be a K.
dt dx. So let's pretend this is an element here, the red with the length L, and the inside is here, and outside's here. So which way is heat going to go? Yeah, because it's warmer inside, right? Okay. And therefore, what is the temperature distribution going to look like on this section of the element? Can you give me the correct engineering relationship, Ender? Not linear.
What does that represent?
The black, the temperature distribution. Just saying it's a linear.
Further.
Yep. Why is it higher on the right than on the left? Because it's warmer on the right than it is on the left, okay? How can can someone tell me what this temperature would be and that temperature in terms of FEM now? Look at our elements here. Sorry, I'm going to zoom out. How did we organize these, left to right? So what should that subscript be for T on the left? T of I. T of I. I'm just helping you try to understand how these things come in. Yep. So why did I do this sketch? Well, go back to the conduction Fourier's law. Yep.
Oh, never mind. You said the TI's.
TI is just indicating any element. Yep. What does the negative indicate in this Fourier's law? Just the direction, right? So technically, we already know the direction, right? So the T of I plus 1 has to be first, right?
Is that to be like small k, or where did the negative go?
So the negative is just to tell you the direction of heat transfer. But we already know the direction, right? It goes from T of I plus 1 to T of I.
Now k is a stiffness. So
Is the no K? Okay, good question.
Reduction to heat or
So it's
resistance
the
to heat
conduction.
transfer?
Yeah, it's the conduction coefficient. Yep.
Oh, okay.
Yep.
Conduction coefficient.
Yep. So just be careful. This K in this conduction equation is a constant, right? It's not stiffness. It deals with the conduction equation, the coefficient. Can someone tell me another way we can write that equation I just did above in terms of resistance? Remember? Some of you probably haven't had this yet, but because R of K is L over KA.
What is R?
R, that's the resistance. We substituted L over KA as R of K.
Were we given that little fundamental equation that RK is equal to L over K?
That's something you should have picked up in heat transfer. Did you? Yeah. So that resistance is corresponding to that resistance.
Oh, yeah.
Okay.
Okay.
Yep.
That was the convection equation?
Yep, conduction equation, not
Sorry,
convection. We haven't done
conduction
convection yet.
equation.
Yep. Okay, what's the convection equation called? There's 4 words. Newton's law of cooling. All right, what's this equation? What's that? HA. Yep. TS is your surface temperature, right? And TF is your fluid temp. Yep. How can you rewrite this in terms of your resistance for convection? Nope. Nope. It's TS minus TF over R sub C, right? And R sub C is 1 over HA. Questions? So now we know conduction, convection that we're looking at. You could also include radiation too, right? Because you know the radiation equation, but make it easier. We don't have to worry about that. So let's go back up to this. And actually, I can redraw it. So in this case, energy is conserved, right? So what does that mean? E dot in equals E dot out. We're going to do a very simple, crude one. So here I have two elements, and I'm looking at nodes 1, 2, and 3. So what I'm going to do is look at what's happening to node 2. So at node 2, energy is conserved. What's coming in to node 2? Energy from the, which one? From the node 3 or the element 2, right? But what is it in heat transfer? Conduction or convection? Conduction. And what's leaving node 2? Convection. Okay? So Q dot K equals Q dot C. So this is sure. So we're looking at that one. So T of I plus 1 minus T of I over R sub K equals TS minus TF over R sub C. We can write that in terms of our T sub 3 minus T sub 2 equals T sub 2 minus T sub 1 all over R sub K2 over RC1. So again, we're assuming I is 2. So here's an example. This is 2 and 3. So the element is between your two nodes.
Element 1 is outside.
Element 1 is outside.
Does it matter which way you go?
Outside air.
Outside air, yeah. Yep.
It doesn't matter which way you went.
What do you mean when?
One's equal to the other one. Doesn't matter if you're going from the outside in or the inside out.
Try to do it the direction the heat's going. So I went from conduction to node 2 because I know what's coming in there and it going out of node 2. Yep.
I'm just used to reading from left to right, so doing it that way. Just
Well,
start at the
so you always have to go the direction of heat transfer.
yeah.
Yep. Okay. How many more equations do we have to do? Well, we already know T1 and T7, right? So 4 more. 4 more, right? If I equals 3, what node are we looking at? Node 3. So we're doing nodes, not elements in this case. So I'm going to give you this to have it complete in your notes. And I might as well do this to have it too. So if you get stuck, you can ask your notes. So here we're looking at node 3. So I wrote the elemental resistance above on the top, so RK2, RK3. And then we have conduction going in and conduction going out, right? So that's why they're sub Ks. And similarly, I think I said that right. Similarly, it's like cinnamon. Node 4. So and I'll write the last two, so you have it complete. And I'll do them right here, side by side. T6, 5, yep. I want it, so when we do this next method, which is the actual like FEM method, where you look at each element, okay, I want to make sure you understand where the elemental equations come from, which are the same as these, okay? They will be the same. There's just two different methods. This method is doing energy balance, right, at each node. What was the problem we did Tuesday? Forces at each node. Okay. So you should have what? 6 equations? 5 equations? And how many unknowns? Should have 5. T2, 3, 4, 5, and 6, right? So I'm not going to write the matrix, but if you have multiple, I'll get right to you. Multiple values, you would have your T through all the way to T6, and then that would equal numbers. This is actually still called a stiffness matrix. This is still called this is called the temperature matrix. And this is called your heat flow matrix. You could call it resistance matrix if you wanted to. Sure. I mean, they're pretty much the same thing. Yeah. Oh, I see. So you could call it resistance, sure. Or you could call it inductance. Yeah, those are all, you're going to have all your resistance values. Yep. Do I want to give that to you now? Sure. What's U? Almost. In our case, K over L.
That's what I was thinking. But I flipped it. Still wrong.
And for convection, it's just equal to H. All right, so let's develop equations for each element. So we're not going to look at the nodes, we're going to look at elements. And we're going to do conduction. Sorry, there should have been a space here. Then we'll do convection. That was not a box I wanted. So we have two nodes here, right? And we have the element. Coming into this element, internally we have Q. Q plus I, Q dot of I plus 1. So coming from that node going into the element is that, and then coming from the element to the other node, we have Q dot I. So just like those internal forces, like we had on Tuesday, okay, here we have looking at the element and looking at the internal forces in this case. So I'll give you the equations and we'll go through them. Bless you. So in a sense, just like the forces, these are the same, right? Q dot I equals Q dot I plus 1. Okay? Just like forces, like those internal forces. Think of it just like that. What did we do with the Q or the F of I on Tuesday? You remember? I'm just going to move this over here. What did we do with F of I? We flipped it, right? To make our life easier. So, in a sense, that's what we're going to do. And what do you have to do with this equation now? Oops. We'll just flip that, right? What's that? Because we want eventually our stiffness matrix that we're going to build to be positive, negative, negative, positive. Okay? And that's how we do that right here. Well, it's, well, they're always equal to each other. So it doesn't matter. Yep. So I'm going to do this in matrix form. Whoa, that didn't work. All right. So does this work out? Q dot I equals T of I over R sub K minus T of I plus 1 times 1 over R sub K. Okay? So it does work. So it does work. So again, we're looking at conduction. Here's the element over here to the right. All right, whatever's coming basically in from this node must equal what comes out of that node through that element. Okay? So the heat transfer coming in and going out of that node, we can define as Q of I dot, or sorry, Q dot of I plus 1 and then Q of I. Okay? And because we know its conduction is related between these two temperature differences, we can look at those two equations, those two temperature differences. Okay? It's the same equation because we know that Q dot I equals Q dot I plus 1. They have to because it's steady state, and that's what we're looking at. So for each element, this is what we're going to have to build. What is this called, this matrix? The number one, or would we call it what else? It's not the displacement matrix. The heat flux, sure. The heat flux, yeah. Is that what I called it up here? Yeah, heat flux matrix, yep. This is your stiffness or conductance or resistance. And then here is your temperature matrix, okay? So we're going to build, this is how you, now we're looking at each element. And how many elements do we have? 6. So this stiffness matrix is going to be like 7 by 7, right? Because you have 7 nodes. Yep. So let's just have this in your notes. So we're going to build this big stiffness matrix. Shoot, erase that. This is a continuation of the same problem. Yep. Let's do convection real quick. So we have that. We're looking at convection because what's the first element? Convection. So our stiffness matrix should have the convection equation. So for a convection elemental Q dot I, what do you think that's going to be? It's H times A times T of I minus T of I plus 1. And what about the I plus 1? Same, but flipped. Yep. Yeah, it's still going this way. But we just flipped the one on the left because to make our life easier. Doing good on time. What? All right, so now we've identified the equations for each element. Okay? And do you have to do these again? No. You now know how to build your stiffness matrix if it's strengths or solids. You're looking at the deflections, which we already did, heat transfer, and actually it's built the same way for everything else. You're going to have two equations. You're going to have positive, negative, negative, positive. You just got to figure out, okay, here we're using resistances, where on Tuesday, what did we have? We had what? We had stiffnesses, yeah. So, yep. Okay, so let's build the stiffness matrix. And this is going to be a big thing. I won't do everything, but I'll do most of it. So what goes in the top four coordinates? It's element 1, right? And what's element 1? Convection. So it's 1 over RC1, negative 1 over RC1, negative 1 over RC1, and are we doing one element or how many? We're doing more than one, right? Because we need to do what here? Is it RC2? RK2. Because this next 4 is element 2. So this would be R negative, right? RK2. Negative 1 over RK2. And this should be 1 over RK2 plus and I'm going to put, to make sure you got this. I haven't finished it yet. Oh, do I? Oh, it should be 5 0. Sorry. Thank you. Good catch. Yep, I just counted my number of zeros wrong. And what color now? Blue? Do 0. There's zeros here, right? And there is 1 0 here.
So it would be 7 by 7.
It will be a 7 by 7. Yep. And I'll put dot, dot, dot. Almost there. There's 7, right?
Is that? Oh, that's the equation for what you're right.
Yes. So this blue matrix, or sorry, this blue equation here corresponds to every element. We've already defined that. Here, what I'm going to show you is we got to apply boundary conditions now. Okay. So what are the boundary conditions? T1 is 20, and then you have 1, 2, 3, 4, 5, and then 70, right?
You know how you have brackets and sometimes you have like the curlicue style brackets?
Yep.
Are those important to keep?
Yes and no. The standard to be T's. Anytime you have variables here, they should be these brackets. If you have a number, it should be that. Over here, because it's equal to that, they use these brackets. Yep. Can someone tell me what goes in the first row in your stiffness matrix? 1 and all zeros. How many zeros? 6. And what about your last row? Yes?
What's the matrix, the stiffness matrix, the bottom left, bottom right corner? Is it just 1 over RC7?
It's not 7. There's only 6 elements.
RC7.
RC6.
Oh, that one.
There's...
Because you know 7 is RC, that's all.
Yeah.
So your bottom right, sure, I could put that in here. Your bottom right 4 will be 1 over RK5, negative 1 over, oh, sorry, plus 1 over RC6, minus 1 over RC6, negative 1 over RC6, and then 1 over RC6. Because there's only 6 elements, because you're only looking at the elements. And then this row should have, like that. Oh. 1, 2, 3, 4, 5, 6 zeros and a 1. So we can basically say that T1 and T7 are automatically going to be 20 and 70.
So, just one more zero.
6 zeros and a 1.
Yeah, you got 5.
Oh. That's easy enough. I always do that. And again, how do we solve for t? What do we need? Yeah, well, how do we do it? We do k to the minus 1 times, let's call it big Q. Sure, or b, whatever you want. Yep. Oh, look, it's already up.
Isn't it? What?
Huh?
It's wrong.
What?
Why was it 20?
Because the 20 and 70 define our boundary conditions. So we're basically hardwiring T1 and T7 to be 20 and 70. And because these are zeros, because there's no heat flux, that's just due to temperature differences. There's no wire that's touching the sides to create a heat flux. All right, so what I did is I defined T1 and T7, my area, and I just picked my values for U. No, it's right in the given problem. Then I made, there should be 6 of these, right? Because there's 6 elements. So my N, I based it off my number of elements in this case. So here's my stiffness matrix. I initialize. Here's my Q matrix. And look, does that look familiar? So I built my stiffness matrix based on the size of my elements.
You don't have, do you have this posted?
I'll post this. Okay. And then what I did here was I set my, because you're doing U, you have to take the area out, so slightly different than what I showed you. All right, but I assigned this value at K11 to 1, and then the n to 1, or 1 over A. Okay, and then I solved it. So let's run this. So here's the solution. Spits it out.